the seminar. So the title is Traces in Non-Semi-Simple Categories, and what I'm talking about is joint work with Asa and Dinov. So usually, if you talk about operator algebras, you will need something which is a C star tensor category, which will be semi-simple typically. So in this semi-simple setting, you will find that there, if you have a rigid structure, then there may be a trace, and this trace is useful because it allows you to assign numbers to morphisms. Now, in the semi-simple case, these traces typically have some very nice properties, like some non-degeneracy properties. And now I want to investigate what happens if you drop the semi-simplicity condition, but you keep some other good properties, like the category has only finitely many simple objects, for example. Then we will see that the standard trace you would typically look at will lose many of its good properties, and one has to look for replacements which are similar to traces, but not quite the usual trace one would know. And I want to look at some of them. I want to start with Hattori-Stallings traces, which sort of the starting point. Then there is a different notion of trace called a modified trace, which can be defined in pivotal tensor categories. We will then look at a special instance of these traces in a more special class of categories, is factorizable ribbon categories. I'll explain what these are. And if there's time in the end, so I'm not super optimistic, but then we will be able to relate this to vertex operator algebra. Yes, so I should also say that most of this is a review of other people's work. The only place where we made a contribution is hidden in this section and in this section. So this you'll probably not even see, but here maybe we'll get to this. So let me start with one. Hattori-Stallings traces. So this is from this is quite old. It's from around 65. So usually, if you learn trace, then you would say you read it in the form that you're given an n by n matrix with entries in some field, say, and then you would define the trace of that matrix, and it's just going to be the sum of its diagonal entries. So from this trace, you know some properties. In particular, it's cyclic. It has a non-degeneracy property if you look at the induced pairing. So this is the first trace one maybe meets when studying mathematics. Now let us modify this situation. Let us say we are given A, which is a K algebra, so an algebra over some field, and we look at an endomorphism of some A module. So let M be an A module, say finite dimensional over K, and this is an endomorphism in here. Now this M is in particular a K vector space, and if we demand it to be finite dimensional as a K vector space, I can look at the trace of this as a linear map on M. So then, if I do this, just the usual vector space trace over M of F, then I get some element of the field. Now, we can ask if that trace is a good way to learn something about endomorphisms of the module. For example, you could ask if you consider a pairing where you take two elements of this endomorphism space, and you define the pairing to be the trace over M of F composed with G. You could ask, for example, is this pairing degenerate, non-degenerate? Well, and what you will find is that in situations where your algebra is not semi-simple, this pairing will be degenerate. Right, and let's look at an example of why this happens, which is maybe illustrative of what is happening. So e.g., if your algebra is polynomial ring divided by x to the d, so this finite dimensional algebra, which is not semi-simple, and we look at the linear map which is given by right multiplication with an element A. So this is the map where you take something of your algebra and you but it doesn't really matter, it's commutative. When I want to talk about left modules, so right multiplication is a natural thing. Then this would be an endomorphism of A seen as a left module over itself. So now if you were just to do the vector space trace of this, so maybe the vector space trace of this, then this only picks out the constant term of A. So this would just be constant term of A. Right? Because all other, so multiplication by x in here will, if you think of a matrix representation of this, be off diagonal. So all of this is not visible. The only term which would be visible here would be the constant term. So in particular, in this example, this pairing here will be degenerate because you can't multiply two polynomials, and so if you're given a polynomial which doesn't have a constant term, you can't multiply it with something to then get a constant term. So the usual vector space trace in this case does not have such nice properties and doesn't allow you to learn so much about endomorphisms. But there is an observation which allows you to rectify the situation at the cost of not being able to consider general modules anymore, but only finitely generated projective modules. So there is a lemma which says that in this situation, A is an algebra over K, then there is a map from A module maps from P into A, and tensor Z over A is P. P is a left A module. I can have a map into endomorphisms of P. And this map simply takes such a morphism here, tensor some element in here, and maps it to the endomorphism of P, which lets phi eat the element of P, that gives you something in A, and with that element of A, you act on this element little p you're given here. Okay, now the observation is that this is an isomorphism if and only if P is finitely generated projective. So you could now use this to try and come up with a new notion of trace. And so for P, so now if P is such a finitely generated projective A module, then this motivates you to try and define the following function on NAP. You would first go to, via the inverse of this map, to hom A PA tensor over AP. Then from here you could go to A, and what this map does is it's just the contraction of these two. So it would take phi tensor P, and you just apply phi to P, so you land in A. So this composition lands you in A. This is not yet what you want, because the overall result should be something which behaves like a trace. This, for a general algebra, which is not commutative, will not yet be cyclic. So then what you do is you just make it artificially commutative by killing commutant. And then this overall composition here, that's called Hattori-Stalin state. Okay. And you can check, well, let me first give a slight modification and then write down some properties. So I want the answer of my trace to lie in the field K, not in A, where I've killed the commutator. So what I will do is I will introduce central forms on A. central forms, C of A is a linear subspace of the dual of A star, with the following properties. So these are all eta in A star, such that eta of AB, A and B elements of A, is eta of BA. Okay, so such forms are called central forms. And so that means that the pairing you construct out of them, where you take two elements A and B and evaluate eta of AB, that is a symmetric pairing. Now, if you have got such a central form, so let's say we've selected some psi in here, then alternatively I could go with psi to k. And by construction, that'll just factor through this. So I have two alternative ways of thinking of the Hattori-Schalling traces. Either I think of them as being parameterized by elements of C of A and taking values in K, or I think of them as this sort of universal object which takes values in A over commuted. Good. So there. So then what properties does this have? So lemma. So this is written for fixed psi, so we fix once and for all one of these central forms. And then we have a cyclicity property. So P and Q are PQ are finitely generated projective. Then if I've got A module maps F and G, then TQ, so maybe I give this overall thing a name, so let's call this TP. So it depends on psi. I dropped the psi from the notation. It's really right, T psi P, but you know, it's understood that I have fixed the choice of psi. So TQ of FG is TP of GF. And secondly, so that's a cyclicity property I have. Secondly, if I pick some finite dimensional vector space X, finite dimensional K vector space, then given my A module P, I can build a new A module by tensoring with X. And I ask H to be an endomorphism of P tensored over K with X. Then, if I compute this Hattori-Schalling trace on P tensor X of H, this is the same as computing it only on P of some other object, namely the object I get when I take the partial trace of H. Let me call this trace the right partial trace, because that's on the right over X of H. So one finds that here I can first trace out this bit and then compute the remaining trace over P. So in this situation, that is, so both of these properties are fairly easy to check. That's sort of a direct consequence of this one. But we'll need both of them in a different setting in a bit. So maybe the final thing I want to say about Hattori-Schalling traces is what happens in my example. So I had this example of the polynomial algebra divided by x to the d. So in example, so I could choose psi such that it is so the largest degree monomial in here, which doesn't vanish, would be x to the d minus 1. And let's say I choose my one form on A such that it's 1 on x to the d minus 1 and maybe 0 or something else on the lower degree monomials. If you do this, then the Hattori, if you use this trace with psi, to compute the pairing, right? So you use, instead of this trace, you use that one. Then you do get a non-degenerate pairing. So this gives non-degenerate pairing on and A. And if I choose psi such that psi of 1 is 1 and psi of x to the I is 0, or I greater than 0, then this will produce the usual trace. So this is a usual trace. So we have a family of traces parameterized by these central forms, which in some cases have particularly good properties, and in others just reproduce what we had before. Yeah, so that's what I wanted to say about Hartrowski study spaces. Any questions?
Excuse me, 2 is not a consequence of cyclicity?
In this lemma?
Yeah.
Yes, it is. So, yes, both.
You can put evaluation for evaluation.
Exactly. So, yeah. So, so in this instance, 2 follows very straightforwardly from 1. But you in your head will already know why I wanted to put this condition, because I'm just trying to write the same one later. So now we get to 2 modified traces. So here I'm following 2 papers. One is by Fujama and Longin from 2010. And another one from Gea, Hatogumi and Yuri in 11. So if you want to see the details of what I'm saying now, it's in there. In fact, the setting in these 2 papers is more general than what I would present now, slightly more general. Anyway, so what we will consider is that C is a pivotal monoidal category, which I want to also be K-linear, case and field, and I want the endomorphisms of the tensor unit to be K. So what does pivotal mean? Maybe I remind what this is a monoidal category means. I've got a tensor product. This means my Hom spaces are K vector spaces, and everything inside is K linear or K bilinear in case of tensor product. And pivotal means that I've got duality, and the double dual is naturally isomorphic to the identity factor in a monoidal way. So pivotal means, firstly, the category is rigid. So I have a contravariant functor from C to C, which assigns to an object its dual, together with a choice of evaluation and co-evaluation. So I have an evaluation X, which goes from X dual tensor X into the tensor unit, and a map co-evaluation X, which does it the other way around, but in different order here. So 1 goes into X tensor X star. So that would be the rigid structure. Now, what is the thing that makes it pivotal is that there is a natural monoidal isomorphism between the identity functor and the functor of taking double duals. And so this is contrary. If I do it twice, I have a covariant functor again, so I can compare it to the identity functor, and that one used to be a natural monoidal isomer. Then the category is called pivotal. So let me say one consequence of this is that you can do traces. So how does that come about? So if I look So I will introduce a graphical notation. Then I can more easily say what is happening here. So for the evaluation, I will just draw this x star x. I draw a little arc like this. My diagrams are read from bottom to top. For the co-evaluation, I will draw a little arc like this. And if I've got these two pictures, then one can easily say what the condition is that these two maps have to satisfy, which I didn't tell you, which is that the two ways of composing this to get the identity is indeed the identity. So let's see. This one here would be going from x star to x star, would be a composition of identity tensor co-evaluation, then evaluation tensor identity, and that has to be the identity of x star. That's one condition on these maps, and the other one is the other way around. So this goes from x to x, and that's the identity from x. Right, so this is again co-evaluation and evaluation. So these two conditions must be satisfied by these two maps for them to form a rigid structure. Okay, so now I want to use this natural isomorphism to produce two new evaluation and co-evaluation maps where the order of the dual and the object are exchanged. So I want to define, say, evaluation tilde, which now starts not with x star x, but I wanted to start with x star. So I can't just contract this because I don't have a map to do that. If my category would have a symmetric grading, I could first exchange the two and then contract, but it doesn't at the moment. But instead what you can do is you can use this isomorphism. So you say I put in delta x here, and then I land in x double star. Now I've got one star more on this side than on this side, so now I can just apply the evaluation for x star. And I will call this evaluation tilde x. And in the same way, we can construct a co-evaluation tilde, which goes now from 1 into x star to x. So we started, and so one way of saying is that we started with right duals only. We have a pivotal structure, and it gives us for free also left duals in a way that the underlying object for the left and the right dual is the same. So now that I have this, I can compute traces, because now I can say take this co-evaluation and compose it with this evaluation, and then I get an element of k. Or I could take this co-evaluation or this evaluation and compose it with this co-evaluation, then I would have another trace. So one of these would be called a left trace, and one would be called a right trace, and I will only consider right trace. Then I stop saying that it's a right trace. Here I write it once to stress that there are two of them. So let f be a morphism in my category, going from x to x. The endomorphism of x, then I define the trace of f over x to be the following diagram. So this is the co-evaluation for x, then I have f tensor identity, and here I have the evaluation tilde for x. And so this now is an element in K, thanks to my requirement that the endomorphisms of the tensor unit I identify them with the field. So I have a map which assigns to endomorphisms of an object x numbers. That is a trace. And I can also do partial traces if I want. Right, so if I have some h, which goes from x tensor y to itself, then I could say take the right partial trace over y of h, and I would define this to mean we've got h, it has one input x, has another input y, has an output y and an output x, and I just do the trace on this length here. So then I get an endomorphism of x in return. So now I will just write on these properties again. maybe I will not even wire well, I just write it out again. So this will also have these two properties. So this trace satisfies that so schematically trace of fg is trace of gf. So you can exchange the order by in this diagrammatic language carrying strings around the loop, but you can translate this into properties of the actual morphisms to see that this works. And it also has this partial trace property, which we've already seen in the Darling's case, namely trace x tensor y of h is a trace over x of this partial trace over y of h. So you can see that sort of structurally it looks similar, but there are some differences. For example, I've got 2 times the same trace symbol here, but here I'm using 2 different traces. This is the usual vector space trace, that was my Darling's trace. And here x and y are of the same sort. They are both elements of the same category, whereas here they are not. P is an A module and x was a vector space. So it looks similar, but also there are slight differences. So having done this preparation, I can finally state what a modified trace is. Definition. So the modified trace will not be defined on the entire category C, but only on some full subcategory I. C. I see the full subcategory, which is at the same time required to be a tensor ideal. So what does it mean? It means if you have an object in I, and you tensor that with any object in C, well, I should maybe say right. I only wanted to point from one side, right tensor here. So you take an object in I and tensor it from the right with an object in C, then you do again get something which already lives in I. So that's the right tensor ideal. And then definition to these people. So a modified right trace, and you can do that for left trace. There are 2-sided traces, but I only want to look at this one. So a modified right trace, which is now only defined on I, is a collection of linear maps, TP, which go from the endomorphisms in C of this object P for all objects which live in this ideal. So the trace is only defined on endomorphisms for objects in this ideal, such that it has 2 properties, namely it should be cyclic, and it should be compatible with the partial trace. So that's the third time I will write this, not very efficient. So for PQ in I and morphisms PF, Q, and G going back to P, I have TQ of FG is TP of GF, cyclicity, and compatibility with the partial trace. So now for P in I, X any object in C, not just in I, and H an endomorphism of P tensor X. I have that if I do this modified trace, I require that the modified trace on P tensor Q, P tensor X of H is the same as the modified trace on P, and then the partial trace in my category, the right partial trace over X, H. yeah, that's the definition. So let's look at this to see if it makes sense. So this
Should we take values in K?
oh yeah, sorry, what did I say? Should go somewhere in my map. Yeah, take values in K. Thanks. So let's see if that makes sense. So P tensor X, thanks to our condition that this is a right tensor ideal, is again an I, so it does make sense to evaluate, to apply this to this. Then over here, this right trace was the one defined in terms of the rigid and pivotal structure of the category, actually down here. So this overall is now an endomorphism of P, and so I can apply TP to it. So the equations make sense, and so this is what I require. So there are now maybe two immediate questions one can ask when seeing this. One is, why would you want to do that? You already have a trace, so why do you want to invent a new one? And the answer to this I will give in the next section when we talk about factorizable ribbon categories. And the second question might be if this notion of modified trace has any relation to the Hattori-Stallings traces I started with. And the short answer, so yes, but not quite as direct as one might hope. So it is not true that the modified trace is a generalization of the Hattori-Stallings trace. Instead, what we have is that both notions are special cases of another notion of trace, which I will just mention, but I'm not discussing it further because I don't need it. But I want to make, at least show that there is some connection. This seems to think I want to always present something on the screen. Maybe if I erase this board. Yeah. Relation. To Hattori-Stallings traces. So the concept which generalizes both of these are traces over module categories. So consider so what's a module category? So we have C, our monoidal category, and a C module category is just the notion. So if you think of C as being categorification of a ring, then a C module category is the categorification of the notion of a module over a ring. So here what you have is it's a functor from M times C into M, together with coherence isomorphisms, which satisfies the conditions you would write down anyway if left alone in a room. So that's a module category. And I claim that, so now you can try to define a trace on M, which has some compatibility condition with C. And let's see how this would fit into the Hattori-Stallings trace. So there, the category M would be, let's call it A prod, finitely generated projective A modules. That would be M. And now this should be a module category over some monoidal category, and the monoidal category is vect. So C is vect in this case. And in the modified trace, the role of M is played by this ideal, which disappeared. So I is a C module. And this map here would then just be the tensor product in C. If you take something in I and you tensor it with C, you end up again in I. And so now from this, you can guess what the structure of a trace on a module category is. You would just write down the same axioms, which are hidden. So they are still these axioms, right? But whenever you read I here, you will just write M for your module category. So this notion of traces module categories has been developed by Schaumann. 2012, so in a slightly different setting. So his axioms include an additional non-degeneracy condition, and the idea is the same. Good. So that's relation, but now I want to work with these modified traces, and I want to say why it is a good idea to introduce this complicated notion, even though you already have a perfectly nice trace in a pivotal category. So now, see, factorizable finite random categories. And I have to explain these words a bit to make clear which setting I'm in now. So K is a field, but not only that, I want it to be algebraically closed. And later, at various points, I will also want it to have characteristic 0. And then C is something more special than just a pivotal monoidal K-linear category. So it's still going to be K-linear. But now it's going to be a finite random category. And I still want that the endomorphisms of the tensor unit are just K. So ribbon means it's braided. Well, first of all, it's monoidal, it has a tensor product, and we have the braiding, and it has ribbon twists. So this means that you can draw morphisms in here as ribbons embedded in our string. Finite. Finite means that you can, as a K-linear category, you can think of C as being modules over some finite dimensional algebra. So it means as a K-linear category, it's the same as a mod, finite dimensional A modules for a finite dimensional K algebra. But this only as K-linear categories. Right, so this makes no statement at all about the monoidal structure. So there's an intrinsic way of saying this, of which I will take, say, 2 points now. So what are consequences of this? One is that there's only a finite number of simple objects. So the category itself is not required to be semi-simple anymore, right? But it will still have a finite number of simple objects. There may be infinitely many indecomposable ones, and finitely many symbols. So I denote by irreducible, by ir, the set of representatives of such simple objects. And another consequence is that there are enough projectives and enough injectives. I work with projectives. So in particular, each simple has a projective covered in my category. Right, and all of these are finite lengths, so they're finite composition series, all home spaces are finite dimensional, right? So all of this comes out of this condition. So that's my setting. And I want to denote by proj C, the full subcategory in C, which consists of all projective objects in C. Good. So So now I want to point out some immediate consequences of this setting, which are good to know. The first consequence is that this subcategory, this full subcategory, is a tensor ideal. It's automatically two-sided because we are braided, so I will drop left or right, because in the braided setting it doesn't matter. So approach C is a tensor ideal. How would you prove that? You would, P projective means this functor is exact. And so now you would have to argue that P tensor X is also exact. Yes. So you would use duality to move this X to the other side, and it gets a dual. And now you use that your tensor product is an exact functor, which again uses rigidity, and that P was exact to start with. So here would tensoring a projective object with anything again gives a projective object.
I think the author you referred to also asked its closed and split subobject. This is true, yeah, of course.
It is.
It is closed when you take subobject.
Right. So it's so that's hidden in here too. So it's a Abelian.
Yeah.
So it's closed with respect to taking subobjects, and the idempotence is split automatically again because it's Abelian. So right. Yeah, so I'm allowed to apply the setting, but you're saying I forgot to say that before. So here I've all the properties I want. And so that's one. So this is good, it's a tensor ideal, so that's something we want to apply this modified trace formalism. Here is another observation. If you look at the projective cover of the tensor unit, right, so the tensor unit is simple. Because of this, and okay, being algebraically closed. So the tensor unit is simple, and I can look at its projective cover, and I can ask, is the projective cover isomorphic to the tensor unit? And this happens if and only if C is semi-simple. So if your category is not semi-simple, the tensor unit will have a non-trivial projective cover. And that's also easy to see, because if you look at an arbitrary object X in your category, you can always tensor it with the tensor unit by virtue of it being a tensor unit. And now this here, by the first observation, is projective. Right? So this just proves that every object in your category is projective. And if that's true, the category is semi-simple. So this is a nice thing to know. And if C is not semi-simple, so this is the main observation I want to make in this lemma. So take P projective, and take F, an endomorphism of P. And now I can use my wonderful trace, which I have in my category, which comes out of the rigid and pivotal structure. And I can look at trace P of F. And this is 0, always. It's now further requirements. So if you have a projective object and you compute any trace of any endomorphism, you always get 0. So the canonical traces given on your entire category from the rigid structure are super boring on this projective ideal. And I want to explain why that is true. So let's compute, let's just write out the chain of morphisms, which gives this trace. So we start in the tensor unit, then we go to P, tensor P star, that's probably the correlation, P. Then we go with F identity to P star again. And then we evaluate with evaluation tilde on P, and we land in 1. That's the trace. Now, this is projective, so this map here factors through the projective cover of the identity. So altogether, I've got the map which maps the tensor unit into its projective cover and then projects onto the projective cover. if P1 is not isomorphic to 1, this is 0. Because this lands in the socle, and this projects everything out but the top, and so this is just 0. So this is what we want a remedy for with the help of these modified traces. So now I will list some results, and I will indicate bits of the proof of just a few of them. One theorem from the paper I mentioned in the beginning. So Kujava and they show that if we have an addition that if I take the projective cover of the tensor unit, take its dual, and I get something which is again isomorphic to the projective cover of the tensor unit, this is called the unimodular. If there is a simple projective object, so an object, a simple object which is its own projective cover, so simple and projective, under these two assumptions, I can find a modified trace. I mean, not only under these assumptions, so they're not necessary, but they're sufficient. So if I know this, then there exists a modified trace on the projective ideal. And better still, this is a modified trace is unique up to constants. So if there is such a thing, then is a unique scalar a modified trace on the projective ideal. Right, so that is pretty. So we have this canonical subcategory, which is projective objects, and under these conditions, on it we have a canonical up to some overall factor trace. And we look at properties of this candidate. But before we do that, I want to at least give the idea on how you construct this trace. So let P be a projective object and let F be a morphism from P to P. Then we want to to compute a number from this, the modified trace. And the procedure will involve many choices, and then the contents of the theorem is to show that it doesn't depend on these choices and that the result actually has properties I stated for a modified trace. So that's the difficult part. The construction is actually very easy. So you pick an object X in C such that if you take this, so let Q be the simple projective. Q simple projective. So there may be more than one, we don't care, we just need one, so let Q be such a simple projective. And now we pick an X such that we can realize P as a direct summand in Q tensor X. So there's some projection and some embedding such that this composition gives the identity. So we realize P as a direct summand in here. This is always possible because you can always choose X to be Q star tensor P. So you can always achieve this, but it's better to keep X out with this property. And then, having this, you make the following observation. You consider the right trace of the following map. So I want to consider the right trace of x over an endomorphism which goes from qx to qx. Well, I put here f, I walk from here to here with p, and I walk from here to here with e. And this now lives in the endomorphisms of q, which are, because q is simple, just the field times the identity morphism, 1 q. Yes. So I have produced a number. I've started with f, done some choices, and produced a number. And now the claim of the theorem is that this is a modified choice, independent of the choices, and satisfies all the things you want. And you can also see that this will not be identically 0 on the projective ideal, because if you choose p to be equal to q, then you can choose x, just the tensor unit, and then you can take the trace of the identity, and you will just get the identity. So this trace does not vanish on the projective ideal. So that's one observation we need. Now I have to explain this word in the title factorizable. And I do this with a combination of definition and theorem. So the theorem part is due to Shimizu from 2016. And the statement is that C is factorizable if any of the following equivalent conditions hold. So the theorem part is that these conditions are equivalent, and I will not even actually list them all. I will just list 2 of them. So the first one is that the only transparent objects in C are direct summons of the tensor. So transparent objects in C are all ISO to some direct sum of tensor units. Maybe I should say what a transparent object is. Transparent object. T, an object is called transparent if you do a double braiding of T with any other object X, or X, and you just get the identity on T times X. So the double, so that is a reason to call it transparent, because you can pull a T string through any other string. So the double braiding becomes the identity with any other object X. So what this means is that the factorizability condition is a statement that your braiding is as far away from being symmetric as somehow possible. I can say that. So then the second condition is if you take the linear product of C and C with reversed braiding, and this, then there is a canonical map to the Drinfeld center of C. And the condition is that this canonical map becomes an equivalence. So that's another calculation of factorizability. And these involve some coend L, and I will not talk about them. There are 2 more conditions. In practice, these are useful, but they are a bit more technical. So what are 2 important examples? Just the main examples of these factorizable categories. Running out of time. Well, let's see. If you add the condition that C is semi-simple, so C factorizable and semi-simple, and all the conditions are just erased in the beginning for C, so written. And so on, linear. So if C is factorizable and semi-simple, then that's just the same as saying C is a modular tensor category. These are useful because they give rise to 3-dimensional topological field series, And there are also some versions of TFT you can construct out of factorizable series, and so that's interesting. So that's one reason why these are interesting. And the other, so modular categories are examples, semi-simple examples, so they drop, so they sort of miss the point of this working for non-semi-simplicity. Another important example is if H is a finite dimensional Riemann-Roch algebra. So it's a Prof algebra, it has an R matrix, it's quasi-triangular, and has a ribbon element. R matrix. Of my Prof algebra then, so the ribbon bit I need to be in the setting which I was with ribbon categories. So then H factorizable, which was defined before in Prof algebras. It's in fact the reason why some people use the name factorizable for these categories, because Prof algebra for factorizable. That's just defined to mean that if I look at the element M, which is R to 1 multiplied by R, element H 10 by H, tensor Hopf algebra, this is a non-degenerate copairing. That's the definition of the Hopf algebra being factorizable. And then you can prove that's the same as rep H being factorizable. In one of these equivalent definitions I've given there. So this, because H doesn't have to be semi-simple, is a source of non-semi-simple factorizable categories. And well, I still want to get to the actual point I want to get to. Who is in? Can I have 5 more minutes? Sure, that is okay. So I want to write a number of theorems. So if H is one of these, so H is this thing, so factorizable algebra, then rep H is unimodular. That was also proved by Lubashenko in '94. And if the characteristic of K is 0, in addition to it being algebraically closed, then rep H contains a simple projective. That was proved by Cohen and Westreich. So in this situation, for such Hopf algebras, you do have a modified trace on the projective ideal. Now what happens if you, so this makes you hope that this maybe holds in this factorizable category setting in general. And so this is indeed true. So let's see the factorizable. Then C is unimodular. That was proved by Ettinger, Nikšić, and Oskar in '04. And if characteristic K is 0, then C contains a simple projective object. And that finally is the joint work with Azad Rainutinov and myself from this year. So also in this general setting, you are guaranteed to have a modified trace on the projective ideal. So these two results are in a way remarkable because the factorizability condition says something about the braiding on your category, right? And yet this implies that something on the block structure of your category, namely that there is a simple projective object which would be like a block on its own in this category. And so that's surprising that these two things have something to say to each other. but it's still true. And yeah, well, I'm a bit out of time, so I will not tell you how to prove this. It's actually quite easy. It's sort of easy in the sense that you just have to combine a number of known results in the right way, and then you get this. Maybe I can say two more things about this. So we have now got, whenever we have one of these factorizable ribbon categories, characteristic 0, then the ideal of projective object is equipped with a canonical structure, canonical up to a scalar, which is this modified trace, TP. And you can show that this modified trace gives a non-degenerate pairing between all Hom spaces of projective objects. So if you look at morphisms in your category from P to Q times morphisms back from Q to P, where Q and P are two arbitrary projectors, I call Q the simple one, P prime. These are all projective, then you get something which lends in K, where you take F, G, and you map it to trace of F composed with G. So you can show that this pairing is non-degenerate. So not only do you have a modified trace, but it's also maximally nice in the sense that it gives you a non-degenerate trace. So when passing from the semi-simple to the non-semi-simple setting, previously you had the trace which comes from the rigid structure in the semi-simple setting, it would just coincide with the modified trace, by the way, up to a constant possibly. And it had this non-degeneracy properties. But now if you pass to non-semi-simple examples, then what you should do is you should look at the projective objects. And these behave as nicely as your as the objects in your semi-simple category before, and that you also have these trace objects. Yeah, and there is some connection to vertex operator algebras, which I will not explain. That's all I want to say. Thank you very much.
Questions or comments for the speaker?
Do you know an explicit example not coming from ribbon of algebras?
Well, there are the examples which come from the quasi.
Okay.
That gives me an excuse to talk a bit more. So if C is this category, you can look at its Frobenius Perron dimensions, the Frobenius Perron dimensions of its objects. And then there's the result that if the Frobenius Perron dimensions of the simple objects are integers, then this is representations of a quasi of algebra. So the question is, do I know an example where this doesn't happen, and which is not also semi-simple, because in the semi-simple case, of course, there are examples, right? So, the answer is maybe, and the maybe is that there was there is a paper by Gelaki, and I think he worked out an example where one of the dimensions is not an integer, but the category is not semi-simple. But I haven't studied this example in general. So yes, that would be an interesting thing to look at.
Do you really need ribbon, or can you do this very quick?
Well, I want it to be braided. Well, it depends what you want to do, yes? So,
I mean, for your theorem.
The theorem, as it is proved, certainly needs very crucially that it is ribbon. I don't see how to modify it. The proof relies on you looking at this endomorphism of an object.
Yeah, but you need the monodromy. But
right. So, okay. So you can ask, if you replace braiding by there being a monodromy, does it still work? And that may be. We didn't study, so that may be. But this is an important thing, and you need to appeal to other results in the literature which were proved in the braided setting. So you have to go through all of them and see if they can be fixed, where you only have a monodromy, and we didn't think about this.
When Chern proved his results on the Chern connection, he used a trace with coefficients. So you got a map from V to V tensor M, trace of that is then an element of M.
Yes.
And it would be terribly nice to generalize ways of doing this. Do any of these constructions shed any light on that?
I have never looked at the proof of germ, so I wouldn't know. But you can look at it and tell me if that's true. Yeah, I don't know the answer to that. That's a good question.
Maybe I shall have a chat with you later about it.
Anyone else? Let's thank the speaker again.